So, uh, welcome everybody. And if this is your first time um, in this place, this is usually what we do. We have most of the time, you have some very specific concepts that we want to discuss, that I want to discuss with you, and also most of the time, it's just this moment is just for me an occasion to kind of provide my ideas on some specific topics, especially related to geostatistics. So, what we will be discussing today is how confident we are with the idea of having a covariance function for intrinsic, well, a covariance model for intrinsic random functions in the form of, a summation of cosine functions. I know you pretty, like, most likely you know what I'm talking about, but if you don't know, um, when you think of intrinsic random function of an order m in the cycle or the sphere, there is this very generic uh specific form of random functions, which is like a sum, an infinite sum of cosine function multiplied by a factor. And so um of course you can look at that definition, or you can look at that theory in terms of, I mean, mathematically speaking, in terms of what is the set of components that took us to that point, right? Like how do I get there? Like, imagine you want to think of a covariance function in the sphere. How do I go from what I know about covariance, what I know about random functions of intrinsic random functions of an order m, to get to the specific form of, covariance function that will be used to run maybe a simulation process or a simulation algorithm. Today, what we are trying to do here is not really going through the proof of that, or going through the development of that, but today I just wanted to I just wanted to step back a little bit and take some time just to show you something really interesting, which is I was looking at the data. I mean, I have a data set that I'm working with most of the time. Is something I use for testing ideas, testing hypotheses. And so I have this data set I was working with, and then I remember I was reading that paper about intrinsic random functions. I saw the form of the covariance model, and I was like, I'm pretty sure I've seen something similar before. And so what happened is, this model that you see here is just basically an experimental variogram computed from a data set in which you have surface elevation in space and time for a specific region, and that is like I think 1 square kilometer, 1 kilometer square region, but the data set is collected in space and time. So of course, it's surface elevation from an ice sheet. I didn't mention it, but I'm sorry. It's surface elevation measured from an ice sheet. So basically, you have an ice sheet changing in space and time, and the relationship between the observation in space and time, it's a non-stationary process, basically. So now what happened is, you compute the experimental model from the experimental variogram from the data set, and you have this green curve, which is, to me at least, it looks like you have some ups and down. And all of a sudden I was just thinking about the general form of, the covariance functions for intrinsic random functions of a specific order. So that's why I wanted to have this today. I wanted to have this today just to tell you one thing is, I believe that development is pretty strong in the sense that, I mean, in theory, you can use that you can sum up different cosine functions to reconstruct something that is something that has this type of pattern, right? Something that has a pattern of, going up and down. Even if the amplitude is changing, you can always find a way to combine different cosine functions to kind of match that amplitude variation, like decreasing over time. And if it's not decreasing over time, you can always find a way, if you sum up different cosine functions, to get as close as possible to this green curve. Obviously, I'm not doing a great job right now. If you look at the red curve that I have, it's not really doing great in terms of, reproducing the green curve. But I was like the reason why I was interested in this is, at least it helps me understanding that the development about intrinsic random function in the circle is not just something that someone came up with based on some um you know pure uh fantastic ideas, right? At least I have something that is consistent with that development. And so now I'm just thinking, I mean, for this one, for example, I was using Euclidean type of simulation. So basically, all I'm doing right now is in an Euclidean space. But what if I just decide to switch to running the simulations in the circle? Now, what are the implications of deciding to do that? Basically, I will change the form of my estimator, because if you are in the circle, it's not the same estimator as what you have in an Euclidean space, just because in the circle you will have to do some additional, factor. Well, it's not really a factorization, but it's basically like you have a random function that you you try to express in a different base. I don't want to say in the spectral domain, because then someone will say, oh, maybe this is something similar to continuous spectral algorithms, which is not. I have an episode of these videos where I was talking about the difference between running continuous spectral algorithms for simulating random function, intrinsic random functions of another M, and simulation of those functions in the sphere. Those are very different. Those are two different things, right? And so I don't want to be talking about the spectral components right now, but basically this is exactly what you're. So the development of these function in the circle is basically like, you think about it as you have a signal, and when you look at a signal in terms of Fourier series, or like in terms of summing different Fourier components, basically what a signal um is you have a scale factor, which is well, if the signal is zx, that's going to be z naught, maybe z0 or zo, and then you have those frequency components that you sum up together to reconstruct the signal. And in other words, it's basically, I have a component that gives me the big like the scale of my signal, something that gives me like the level of my signal, and I have something that gives me information about how that signal is varying in in its domain, right? If it's a temporal domain, then how it's changing in time. If it's space, how it's changing in space. If it's space time, how it's changing in space time. So yeah, so technically those two, like spectral continuous spectral algorithms and the simulation of intrinsic random function of order M in the sphere or the circle, those are two different things, right? But the reason why I wanted to show this is, I wanted to say that if you really have a data set where uh, most likely the random function is non-stationary, chances are, if you compute the experimental model and you want to see how it looks like, you will probably end up with something that has a shape of a sine or cosine function, which is good, because then it will take you to that development where they said most of the time the general form of covariance functions or intrinsic random function is this sort of it's a combination of cosine functions. So that's why I wanted to show you this. And, yeah, obviously I